Hello friends, welcome back to my channel, A Physicist Buddhist. So earlier I posted a short video about this book, Quantum Mechanics, Principles of Quantum Mechanics by Paul Dirac. So today I'm going to talk, in this video I'm going to talk in a little bit more detail about this book. So like I said in my earlier lecture, this is one of the classic books of quantum mechanics, probably the best book ever written about quantum mechanics, and so I'm going to talk in more detail what this book is about and why is it so famous and why is it has proved to be so useful in teaching quantum physics to several generations of physicists. So Dirac was, like I mentioned earlier, was one of the founders of quantum mechanics. In 1928, he made his seminal contribution to quantum mechanics when he predicted the existence of a particle known as positron, which is the antimatter partner of electron. So around that time, Dirac started working on his book, which he published in 1930. In this book, he presented his thinking about quantum mechanics, right, going from the beginning, how the quantum mechanics came to be, and the basic ideas of quantum mechanics, the principles of quantum mechanics, the mathematics that's needed, and a lot of that was created by Dirac. I will talk about that later, and all the way to the applications of quantum mechanics to different aspects of quantum physics. Okay, so let's start with the beginning of this book. So I'm going to show the book. I hope you can see that. It is Principles of Quantum Mechanics by Paul Dirac. So this is the final version that Dirac completed in his lifetime. It was published in 1968. So let's talk about this book, starting from the beginning, what Dirac talks about and how he lays out his view of quantum mechanics. So he starts with the principles of superposition. So that is the fundamental principle in quantum mechanics, which basically makes the phenomenon of quantum entanglement possible. So one of the most fascinating features of quantum mechanics is quantum entanglement. So, and where does that quantum entanglement comes from? It comes from the fact that the equation of quantum mechanics that Dirac came up with, which is known as Dirac equation. Incidentally, this equation is what also predicts the existence of antimatter particle, positron, like I talked about earlier. One of the solutions of this equation predicted the existence of positron, which was discovered 3 years later in 1931 by an American named Carl Anderson at California Institute of Technology. So the principle of superposition underlies the whole idea of quantum entanglement. So since the Dirac equation is a linear equation and it's a relativistic invariant equation, but this was the genius of Dirac, that he understood that in order for the relativistic equation to describe the behavior of electron, it has to have the same order of derivative with respect to space and time. So unlike Schrodinger's wave equation, which came 2 years before, 1926, in Schrodinger's equation, the derivatives of space and time are not symmetric. So Schrodinger's wave equation has a second order derivative for space but first order derivative for time, and that's why it does not predict the existence of spin. So in Schrodinger's wave equation, the spin has to be added by hand, so to speak. So Dirac basically came up with this idea that if you have an equation which is symmetric with respect to space and time coordinates, then the derivatives of space and time coordinates, then it would predict the existence of, and that's what Dirac did. So his equation is a first order equation in both space and time coordinates, and the solution of this equation gives us the spin of electron. Okay, so this is what and then right after that Dirac started working on this book, and which he published in 1930, and in this he lays out his vision, and he also describes his equation and how to solve it. And so to go in the order in which the contents are listed, so he first talks about principle of superposition, like I said, dynamical variables and observables. That's what he talks about next. So basically in quantum mechanics, anything that can be measured, it's an observable, and it corresponds to a variable which is known as dynamical variables. Some of these are position, linear momentum, time, energy, etc. So these are the dynamical variables. Then Dirac talks about representation. So Dirac came up with his own way of representing the functions in quantum mechanics, which are known as eigenfunctions, and so he came up with these vectors, which are now known as Bra and Ket vectors. So they are called Dirac's Bra and Ket vectors to describe these eigenfunctions in quantum mechanics. And then Dirac talks about how one goes from classical mechanics to quantum mechanics. So basically it's a straightforward process. So in classical mechanics, the dynamical variables are described in terms of Poisson brackets. In quantum mechanics, they're described in terms of commutation brackets. So going from Poisson brackets to commutation brackets takes us from the classical physics to quantum physics. Now, and then he talks about the Schrödinger version of quantum mechanics and Heisenberg's picture of quantum mechanics. And of course, if you count Dirac's picture also, then there are three. So incidentally, they shared the Nobel Prizes for 1932 and 1933. So the Heisenberg got the Nobel Prize in physics for 1932, and Dirac shared the 1933 Nobel Prize with Schrödinger. Anyway, coming back to the book, so then Dirac starts to talk about the applications of quantum mechanics, and the first example he talks about is the harmonic oscillator and angular momentum, and of course the spin, which his equation for the first time actually allows to be obtained from the equation. Okay, then Dirac talks about perturbation theory. So most problems in quantum mechanics are too complicated. They cannot be solved exactly except the hydrogen atom. The hydrogen atom is probably the only problem in quantum mechanics, which is one body problem, one single electron, which can be solved exactly. So all other problems one has to do some approximation method. So there perturbation theory comes in very handy, and there are two types of perturbation theories: time dependent perturbation theory and time independent perturbation theory, and Dirac talks about them. And then the problems of collision. So basically one of the most important thing in particle physics is to calculate the scattering cross section. So when two particles scatter, so one particle is coming here, and so how they scatter, which is basically you want to calculate the quantum mechanical amplitude of the scattering. So because these are quantum mechanical quantities, so their scattering amplitudes have to be calculated quantum mechanically, and that's what quantum mechanics allows one to do that. Okay, so then Dirac talks about the theory of radiation, of course. So the whole universe consists of two things. So when you say what's universe consists of, the two things are matter and radiation. So the stuff that you see around you, the paper, the pencil, the table, the chair, the body, these are all matter, and the light that is streaming in through the window, it's radiation. So the quantum mechanics has to basically do three things. It has to provide an exact comprehensive method to calculate the properties of the matter. It also has to do the same for the radiation, and then, which is the most difficult part, when the matter and radiation interact with each other. Okay, so and quantum mechanics does that. So then Dirac moves on to relativistic theory of electron, and it turns out that electron basically when it's created, it's a relativistic particle. Relativistic particle is something that's moving at a very, very high speed, close to the speed of light. So the behavior of that particle then has to be described in terms of Einstein's special theory of relativity. That's what is called relativistic electron. Okay, so the relativistic effects come into being. The mass of the electron goes up. It's the time basically dilates for the electron because of the relativistic time dilation, and so these factors have to be taken into account in describing an elementary particle's behavior, for example, an electron. And then we come to the last part of the story, which is quantum electrodynamics. So what is quantum electrodynamics? So this particle, this electron that I talked about, which is moving at close to speed of light, so it is because electron has charge, and a moving charge creates a magnetic field, and it also has an electric field. So basically the relativistic electron has an electromagnetic field which is associated with the electron itself, and it interacts with its own electromagnetic field. Now this is the most fascinating, one of the deepest and most fundamental and subtle parts of quantum physics, that an electron interacts with its own field, and that interaction changes the electron. Okay, it changes the mass of the electron and the charge of the electron, and these facts are all these components are gathered together in this theory known as quantum electrodynamics. In my previous lectures I talked about quantum field theory. So quantum field theory basically, quantum electrodynamics is just one type of quantum field theory. So this basically is the same thing that I talked about earlier. So it's a very complex, very mathematically formidable and subtle theory, and so the idea is to be able to calculate the properties of an electron which is interacting with its own magnetic field while it's moving at relativistic speeds. So you have to apply quantum mechanics, you have to apply Einstein's special theory of relativity, and you have to take into account the interaction of an electron with this electromagnetic field. Now electromagnetic field, like I said earlier, that's what radiation is. So the light is nothing but another type of electromagnetic field. So radiation is electromagnetic field in this context. So we have matter, which is electron, we have radiation, which is electromagnetic field, and we have interaction between the two, and all three combined together in this theory called quantum electrodynamics. And like I mentioned in my earlier lectures, this theory was had lots of mathematical problems. It basically, even though nothing in physics, like especially a small particle like electron, should not give any infinite values as answers, but in quantum electrodynamics, that's what people noticed, that it was basically giving ridiculous answers. It was basically giving energy that was infinite, and so on and so forth. So it took a long time for people to figure out how to remove those infinities through a program called renormalization, which was completed in late 1940s by American physicist Richard Feynman and Julian Schwinger and a Japanese physicist Shinichiro Tominaga. So all these people built upon the foundations which were laid by Dirac, Heisenberg and Schrödinger back in the 1920s. I think I would stop here. You found my lecture interesting and intellectually stimulating. So if you like my lecture, and if you would like me to make more lectures on this subject, please let me know in the comment box below. I'll be happy to create more lectures for you. Now, thank you for your time, and have a good day. Thank you.